Let us continue our discussion from the previous lecture, that is on the topic of K-maps or the Karnaugh maps. In the previous lecture, we discussed primarily about the two variable logic functions and how you can construct their K-maps and solve them to obtain the minimized logic expression in both SOP form as well as POS form. From now on, a large part of our discussion would be limited to the SOP form because the concepts for SOP and POS are pretty much analogous to each other. So, in this particular lecture, let us look at the K-maps in more detail by seeing how we can extend them to solving for the 3 variable and 4 variable logic functions. So, without further ado, let us assume that we have some kind of a 3 variable logic function which looks kind of like this. So, let's start numbering. Let us also give a row number which will go from 0 to 7. Let us say the output looks something like this. Something of this kind. So if we were to now list the minterms are which are ones. So if we want to realize this function in the SOP form, what we can do is look for the ones. So therefore I can write it in the canonical form this way. The condensed canonical form, that is the sum of the minterms which are numbered 0, 4, 5, 6 and 7. Now, the principle for the K-maps of a 3 variable function is pretty much the same as that of a 2 variable function. The underlying principles do not change. However, you need to be a little bit more watchful when you are solving the K-maps for functions having more than 2 variables, and I'll tell you why. But before we go for that, let us try to see how to construct a K-map for 3 variable functions. So, as you know, based on the previous lecture's knowledge, we know that the number of rows will be equal to the number of cells of the K-map. So here there are 8 rows. So therefore even the K-map will have 8 cells. However, this will now not be a square table anymore. If you recall, the 2 variable K-map had 4 cells and that could be nicely drawn in the shape of a square. But the same cannot now be done for 8 cells. So the best way to do is to have a 4 into 2 or a 2 into 4 layout, because as you know, the axes indicate the variables, so they will always be in some power of 2 as far as the values they can take are concerned. So therefore, let us try to draw. Now, we have 3 variables and we have 2 axes. So, one axis will be for one variable and the other axis will be for 2 variables. So, therefore, let us put A and B for the horizontal axis and C for the vertical axis. So, this we can say C bar and C. Just like how we have for a 2 variable K-map. Now, the first thing that we have to check, or the first thing that we have to do, is to assign the cell numbers. Now, we have to be a little careful. Notice that this is a 4x2 layout. So, the numbering has to be done from 0, 1 all the way to 7. This is the cell numbering. So, we cannot just keep saying 0, 1, 2, 3, 4, 5, 6, 7. Well, that's not how it goes. Remember how the K-map has to be constructed. The K-map has to be constructed by obeying the implicit gray code. That is, the neighboring cells, neighboring vertical or horizontal cells should differ by only 1 bit position. So therefore, let us start with what we already know. Let us say, using our knowledge of the 2 variable K-maps, let us call the first as 0 and this one as 1. Right? So 0 will happen for the SOP when it is A bar, B bar and C bar. So this row we can label it as A bar and B bar. And this is also valid for 1 because A bar, B bar, C indicates 0, 0, 1. Next, let us write 2 and 3 over here. Will it satisfy? Yes, because 0 and 2 are still differing by 1 bit position. So therefore, 2 will be A bar, B, C bar. So this will be A bar, B. And 3 will be A bar, B, C. So this is also valid. A bar, B, C indicates 3. That is 0, 1 and 1. Now comes the fun. What will be the number of this cell? Will it be 4? Well, logic tells me, let us say we'll try to name it as 4. But then we have to see, are 2 and 4, can they be neighbors? But 2 and 4, they cannot be neighbors. They cannot be neighbors because 2 is 0, 1, 0, 4 is 1, 0, 0. So they are differing by 2 bit positions. So now we need to ask ourselves, after 2, which is the higher number that differs by 1 bit position? Not 4, not 5. 5 differs by 3 bit positions. 6, yes, because 2 is 0, 1, 0, 6 is 1, 1, 0, where only the MSB is different. So this we can number as 6. Let me repeat. We are considering this cell number 2. Now we have to check which is the next number above 2 that differs in only 1 bit position. 3 is already marked, so we will not consider that. 4 differs from 2 by 2 bit positions, this one and this one. 5 differs from 2 by 3 bit positions, all of them. But 6 differs from 2 by only the MSB position. So therefore, this I am numbering as 6. Likewise, this one, this cell number has to be such a number which differs from both 3 and 6 by 1 bit position. Now 2 is out of the picture. Both 3 and 6, it has to differ by 1 bit position. 3 is 0, 1, 1. 6 is 1, 1, 0. So if I have 7, that is 1, 1, 1, it differs from both 6 and 3 by only 1 bit position. So this will be 7. So in terms of the variables, 6 is A, B and C bar, whereas 7 is A, B, C. So this column will be labeled as A and B. Because A, B, C bar is 6, A, B, C is 7. Now what is left? These two. Obviously, instinctively I will know it is 4 and 5. But let us verify it. This cell number has to differ from 6 in only one bit position. 6 is 100. So 5 cannot be here because 5 differs from 6 in 2 bit positions. So this has to be 4. And for the variables, 4 is A, B bar, C bar. So we will name this as A, B bar, and 5 is A, B bar, C, which is this. So we are done. This is how you construct a 3-variable Karnaugh map. Now, the next thing is to fill up the minterms. We have to fill up those cells where it is 0, sorry, where it is 1, the output. So the 0th cell, 4th, 5th, 6th and 7th. So our K-map is filled. Now let us solve the K-map. We have to now group these ones. So as you know, we have to group with vertical and horizontal neighbors only, and the group size can be, or the group size rather, should be as large as possible and in a power of 2. So what I can see, 4, 5, 6 and 7 are all vertical and horizontal neighbors to each other. So immediately I can make a group of 4 over here and call this as group number 1. I can call this as group number 1. There is one more 1 left, which is over here. Now this poor fellow is away from all of these. This poor fellow is away from all of these ones. So therefore, it seems that this one cannot be grouped with anybody else. Wait, that is not the case. This is why I said you to be a little bit more watchful when you are dealing with K-maps of variables more than 2. Let us look at 0 and 4. 0 is 0, 0, 0, whereas 4 is 1, 0, 0. So actually even 0 and 4 are neighbors of each other. 0 and 4 are neighbors. That is like saying, if you were to visualize that a group starting from here can end over here, I can group this one with this one. The group size will be 2. Similarly, if had there been one more 1 in the first 1th cell, I could have grouped it with 5 because 1 is 0, 0, 1 and 5 is 1, 0, 1. Again, they are differing by 1 bit position, just like 0 and 4. So be very, very watchful over here. You can indeed make a group which looks like this. So it's as if you can, the group will go like this, starting from here and ending over here. So therefore, I will call this as group number 2. So now let us see these two groups, what expressions they correspond to. So as you know, in the groups, you have to see which are the common variables. In the group number 1, which is this 4, B and B bar are not common, C and C bar are not common. What is common is A. And group number 2, B bar is common, A and A bar are not common, and C bar is common. So this will be B bar, C bar. So therefore the answer Y is equal to A plus B bar, C bar. That's it. That's it. Alright. This is how you solve a 3-variable K-map. Let us take one more example, just to show you how different things can be. Let us consider the same function, but with a slightly different set of minterms. Let's say Y is having the midterms at 0, 5 and 7. That's it. That means only in these places we have a 1. So therefore again let us draw the K-map. So now let us number the cells just like the way we did previously. So this will be A bar, B bar, A bar, B, AB, AB bar. So 0 means here there will be a 1, and 5 and 7 here there will be 2 ones. Now immediately I can see I can make a group of 2. Let's call this as group number 1. Now what about this one? This one now is truly alone. There is no 1 over here, neither there is any 1 over here. So this you cannot group. So therefore this one which is all by itself, let me call it as term number 2. This is also called as an essential prime implicant. Just like a prime number which is not divisible by most numbers apart from 1 and itself, a prime implicant is one which that one which cannot be grouped with anybody else, and therefore has to be written just the way it is. So therefore term number 1, if I look at group number 1, I can just simplify it by looking at the common terms. That is A is common here and C is common. So it's A dot C. And term number 2 will be this one as it is, that is A bar, B bar, C bar. So therefore Y will be now equal to A dot C plus A bar, B bar, C bar. And this is the most simplified form that you can extract out of this K-map. Right? So let us, just for the sake of completion, also look at how to solve a 3-variable K-map in POS form. So let us say I have this canonical form. Oops, it's POS, so I have to use product with max terms. These are the max terms, means these will be zeros. So therefore, if you want to construct the K-map, it will still be the same as that of the SOP form. However, there will be certain small changes. So the numbering of the cells will remain the same. So 0 means it is 0, 0, 0. So that means all are 0. That means this will now be C and this will be A plus B. And this will be C bar. 2 is 0, 1, 0. That means A bar plus B. Sorry, A plus B bar plus C. So this will be A plus B bar. So just remember that this will be A plus B plus C. This is A plus B plus C bar. This will be A plus B bar plus C. Likewise 0, 1, 1 will be A plus B bar plus C bar. Like that. So therefore this will now be A bar plus B bar. Again, the gray code has to be satisfied. And this will be A bar plus B. Is that correct? Yes, it is correct. I think so. Yes. So now let us fill up the zeros. So 1, 2 and 3. So we again now have to group zeros. So immediately I can make one group over here and one group over here. Let me call this as group number 1 and this as group number 2. So now let us see what is the term corresponding to each group. So for group number 1, the common terms is A plus B bar. And corresponding to group number 2 is A plus C bar, because B and B bar will cancel over here. A plus C bar. So therefore, Y will be the product of these two, that is A plus B bar dot A plus C bar. That is the answer. This is how you solve for a K-map in the POS form. So I hope this is clear. Let us now move over to something that is a little more complex. That is 4 variable K-maps. Coincidentally, it's page number 4, where we start with 4 variable K-maps. So let us again write a truth table. Let's say there are 4 variables, and let us now fill in the truth table by taking the row number as a reference. So 0, 1, 2. Since there are 4 variables now, the number of rows would be essentially 16. So the numbering would go from 0 to 15. It's the same as a 3 variable. So with this, I'll just teach you a neat little trick to remember how to construct larger truth tables. Consider BCD as a 3 variable truth table and just write it this way, just like a 3 variable truth table. And for all of these 8 rows, the A value will be 0. Now, once again, for the last 3 variables, repeat the 3 variable truth table, just like this. And now the value of A will be 1 for these last 8 rows. Now suppose, let's say the function is 1 where over here These are the entries. So therefore the minterms are at 0, 3, 5, 6, 9, 10, 11, 14 and 15. So since there are 16 rows, the K-map will now be a 4x4 graph, which would look something like this. An expanded 2x2, so now we have two axes. So each axis will be for two variables. So let's say A, B, C and D. Now, once again, we need to approach this K-map very carefully. Now, the reason is primarily to ensure that the gray code is satisfied. So let us consider the first four rows in the truth table, 0, 1, 2 and 3. Over here, A and B are always 0. A and B are always 0 for the first four rows. So therefore, just like a 3-variable K-map, let us name this row as A bar and B bar. So for row number 0, it will be A bar, B bar, C bar, D bar. So if I name this as 0, this will be C bar, D bar. For 1, it will be A bar, B bar, C bar, D. So A bar, B bar is here, we need a C bar, D. So this will be cell number 1. Now let us be careful. Over here, this cell has to be numbered in such a way that it is differing from 1 by 1 bit position. So 2 cannot come because here it is 0001 and 2 is 0010. So it's differing in 2 bit positions. So next we will take as 3 because 3 and 1 differ in only the C bit position. So this we will number as 3 and this will be 2. Notice that for both 3 and 2, it is still A bar and B bar because A and B are both 0. Thus, the variable for 3 will be C and D and this will be CD bar. Notice the order is just like that of a 3-variable K-map from the horizontal axis. In the 3-variable K-map, we had A bar, B bar, A bar B, AB and AB bar. Just like this, we have C bar, D bar, C bar D, CD and CD bar. So just like that, we can do it for this axis also. So this will be A bar B, AB and AB bar. With this, let us now complete the numbering. A bar B, C bar D. That means it is 0, 1, 0, 0. This means it is 4. A bar B, C bar D. That is 0, 1, 0, 1. That is 5. A bar B, C D is 0, 1, 1. That is 7. And A bar B, C D bar is 0, 1, 1, 0, which is 6. Now, A, B, C bar, D bar. A, B, C bar, D bar is 1, 1, 0, 0 and 1, 1, 0, 0 is 12. 1, 1, 0, 1, that is 13. 1, 1, 1, 1 is 15. 1, 1, 1, 0 is 14. You see, the numbering is again changing abruptly. Here, A, B bar, C bar, D bar. That is 1, 0, 0, 0. That is 8. 1, 0, 0, 1. That is 9. 1, 0, 1, 1 is 11. And 1, 0, 1, 0 is 10. This is how you number the cells of a 4 variable K-map having 16 cells. So, now we know the midterms. The midterms are at 0, 3, 5, 6. 9, 10, 11, 14 and 15. So that means the ones will be there. 0, 3, 5, 6, 9, 10, 11, 14, 15. So how can we solve this? Immediately I can say that I can make a group of 4 over here. Let me call this as group number 1. What else can I do? I can make a group of 2 using these 2 ones. Next, I can group 11 and 3. Notice that they are still neighbors. How? 1, 0, 1, 1 and 0, 0, 1, 1. They are still differing by 1 bit position. So therefore, these we can group. I'll call it as group number 3. And what else can we do? We can group 6 and 14. Let's call this as group number 4. Now these 2 ones are still remaining. And unfortunately nothing can be done about these 2 because they have no immediate neighbors vertically or horizontally. So therefore these 2 are prime implicants. So let's call them as 5th and 6th terms. So now, what is the term corresponding to group number 1? The common variables are A over here and C over here. So that is A dot C. Group number 2 is here. The common terms are A, B bar and D. Group number 3 is between these 2. The common terms are B bar, C and D. Group number 4 is B, C and D bar. 5 and 6 are just what they are. 5 is A bar, B bar, C bar, D bar. And 6 is A bar, B, C bar, D. So therefore, Y will be a plus of all of these terms, which gives us Y equal to A dot C plus A B bar D plus B bar C D plus B C D bar plus A bar B bar C bar D bar plus A bar B C bar D. That's it. That's how it is. Let us take one more example of a 4 variable K-map. That is, let us say y equals ABCD function, and the minterms are 3, 6, 8, 10, 11, 12, 13, 14 and 15. Now, let us construct the K-map in the way we did it in the last example. We have A, B, C, B. This is A bar, B bar, A bar, B, A, B, A, B bar. Just like this, we have C bar, D bar, C bar, D, C, D and C, D bar. Numbering, let's be careful. 0, 1, 2, 3, 4, 5, 6 and 7, 8, 9, 10 and 11, 12, 13, 14 and 15. So let us enter the cells where there is a 1. These are the minterms. 3, 6, 8, 10, 11, 12, 13, 14 and 15. Okay, so this is what it looks like. Now, what are the groups we can make? Immediately, I can see there are 4 ones in a straight line. So, I can make a group this way. I can make a group this way. Then, I can make one more group by grouping these 4 ones. So I have 2 groups of 4, which is good. What else I can do? I can group this one with this one. But wait, these 2 ones are neighbors, but they are also neighbors with these 2 ones. Remember, the edge cells are also neighbors. So I cannot just group these 2, but I can actually make a group of 4 ones, these and these 4. Then I can make a group of these 2, and this one I can club it with this one. Right? So therefore let us number the groups. This is group number 1. This long one is group number 2. This edge groups of 4, it's let us say group number 3. This is group number 4, and this edge, these 2, is group number 5. I don't think there are any more groups we have made. No. So therefore, let us write down those terms. So for these, what we will see is group number 1. The group number 1 is these 4. The common terms are A and C. Group number 2, this row. The common terms are A and B. Group number 3, this edge. A and D bar. Group number 4, B, C, D bar. And group number 5 is B bar, C, D. So that means Y is a plus of all of this. This is how you solve a 4 variable K-map. Now, we saw that there are many ways to do this. However, it may so happen that after constructing a K-map, you may definitely find some cases, some functions where you will not find a single, group of ones or zeros for that matter. Because it may so happen that there are no neighboring ones or zeros, either vertically or horizontally. So therefore, it's not always the case that a K-map will give you the simplest form. If there are no ways with which we can simplify, well, that's disastrous. I mean, it's not disastrous, but it's the fact that there's no point in constructing the K-map, and you cannot always know about these things early on. You construct the K-map and then you see that there are no neighboring ones next to each other. Alright, so such cases do happen. So, let us say I have another 4 variable function which is probably not what I would like, that is a form which cannot be simplified. So let us say I have a y which is a function of a, b, c and d, and the minterms are 6, 8, 9, 10, 11, 12, 13, 14 and 15. So in that case, the K-map would look like this. Just like what we have been doing so far. So once again, A bar, B bar, A bar, B, A, B and A, B bar, C bar, D bar, C bar, D, C, D and C, D bar. Alright, so let's start filling in. 6, 8, 10, 11, 12, 13, 14 and 15. How can we solve this K-map? I can here make a group of 8. Remember, larger the group size, simpler is the solution. And finally, I can make one group over here. This is group 1, this is group 2. So corresponding to group 1, the expression will be what? The common terms over here in this group is only A. And 2 will be B, C, D bar. B, C, D bar. So therefore Y will be A plus B, C, D bar. C is outside. So now if I ask you, implement this function using NAND gates, because ultimately as designers we have to have the simplified function in a form which can be implemented using NAND gates. So what we know is that each product term corresponds to a NAND gate. And one more NAND to combine all of these. So therefore, let us see what it means. Now you may question, why one NAND gate for A? So here we will be using the NAND gate as a NOT gate. This is A. Then we have one more gate which is B C and D bar. And then we will be combining them over here with one last NAND gate. Let us verify. This will be A bar. This will be B dot C dot D bar whole bar. So this one Y will actually be equal to A bar B dot C dot D bar whole bar bar. This will be A bar bar plus B C D bar bar bar, and that is nothing but A plus B C D bar. So this is how you implement a simplified SOP form using NAND gates. Now, having established this basis, we will in the next lecture look at those cases where there is no possible solution, which I was mentioning few minutes back. No possible way of grouping any ones. But that is for the next lecture. Thank you.